Good morning, ladies and gentlemen. Our next topic for electrostatics is all about electric potential, which is more commonly known as voltage. But before we actually talk about electric potential, let's compare back to gravity first. Normally, when you raise a book off the ground, 2 meters, of course you are increasing its height, but according to mechanics, we are also increasing its gravitational potential energy. Which you also, of course, knew as UG. And if I wanted to increase the amount of potential energy that it has, I could either increase the mass, because UG is equal to mgh, or, of course, I could increase its height. And the reason that we know that there's potential energy is that if you were to release those blocks from up high, they would fall and ultimately turn into kinetic energy. Okay? So ultimately, the amount of potential energy a mass has is based on its weight and based on its height. Two main factors. Now, we know that charges can speed up also whenever they're placed in an electric field. Okay, just like the masses are speeding up when they're placed inside a gravitational field. But what really determines how much energy a charge has? Well, just like before, when we have a smaller mass, we can have a smaller charge versus a larger charge. A larger charge would have more potential energy stored in it. And we have the same idea of the charge falling down through this distance. When it falls down, it's gaining a certain speed, and it gains potential energy. It gains kinetic energy. So in this case, there's a location of high potential energy. One's near the top, and of course, there's going to be low potential energy near the bottom, but all that potential energy turns into kinetic. But one of the key differences between gravity and electrostatic forces is that, of course, there are two types of charges. And because there are two types of charges, they act a little bit differently. If I were to place a negative charge over here at the top, would it go anywhere? No. Okay? It wouldn't have any, it would already be stuck to that top plate. So rather, if I put that negative charge at the bottom, then at the bottom, when it's next to its own charge, we have a location of high potential energy. So whenever a charge is near its own like charge, it's going to speed up. So in this case, it has a location of high potential energy. It loses that potential energy by the time it gets to the top, but it's speeding up, so it turns into kinetic energy. So positive charges, of course, will go towards negative. Negative charges will, of course, go towards positive. So we can see that the strength of the charge plays a factor in determining how much energy there is. Okay? Before is UG equals to mgh. Whenever I'm talking about UE, okay, the energy stored in an electric field, rather than dealing with weight, I'm dealing with charge. But what's the equivalent of height? I mean, I know I have this distance over here, and that technically could be considered the equivalent of height, but what if the plate had a stronger positive charge on it and a stronger negative charge? Then if it's even stronger, then the electric field would be stronger, and the charges would accelerate even faster than before. So it's not just the distance that plays a role in how much it's going to speed up, but also the strength of the charge on the plates that plays a role in how much it's going to speed up, because it creates a stronger electric field. So before we actually move on, let's actually take a better look at parallel plates themselves. Okay. So this is on a page further in your packet. What is so special about the electric field of parallel plates? Of course, we know that the electric field of parallel plates are constant within, and because the E is constant, we know, of course, as we said before, that the Fe on a charge is constant also. But ultimately, what determines the strength of the electric field inside a plate? And the reason those plates are charged in the first place is because they're connected to some sort of voltage, some sort of battery source. So in this case over here, the formula for this would be E equals to V over D. Really, it's delta V. I'll say that for now. But E, of course, is the electric field. D is the distance between the plates. And V is the potential difference, the electric potential difference. And we'll talk more about what that means in a moment, but take a quick look at this picture over here. Okay? So we have our parallel plates. Now we're looking at more of a three-dimensional model. We can see that the top plate, of course, is charged positive. The bottom plate is charged with a negative value. It's connected to some sort of battery source on the other side. And that battery source will create an electric potential, a positive electric potential on one side. So let's say this is a 10-volt battery. Okay? So that means that on the top plate, it creates an electric potential of positive 5 volts, and on the bottom plate, it creates an electric potential of negative 5 volts. So overall, the potential difference between the two plates, delta V, would equal to 10 volts. What does it mean to have an electric potential? We're going to discuss that more in a moment, but I just want you guys to understand, if you attach a stronger battery to it, you will have a stronger electric potential, and there's a greater potential difference. So in this case, when you do E equals to V over D, or really delta V over D, then the strength of your electric field is determined based on that. So if you bring the plates closer together, your electric field gets stronger and stronger. And the other way to strengthen it, of course, would be to attach a stronger battery to it. So if I were to do a quick practice problem with that, two parallel plates are charged to a voltage or a potential difference of 50 volts. The separation between the two plates is 0.05 meters. So E is equal to V over D, or delta V over D, which equals to 50 volts divided by 0.05 meters, which in this case will equal to, let's see, 1,000. Now, our previous unit for electric field was newtons per coulomb, and that's based on the formula E equals to F over Q. So we get newtons per coulomb from that. However, based on this formula, we can have an alternate unit. Either one is fine, but in this case, it could be volts per meter. Okay? So just a quick, simple practice question demonstrating electric field. Okay, so if we go back to this picture over here now, when we are talking about UG equals to mgh, the weight times the height, so we have the weight, which is mass times gravity, times h. Overall, there's going to be some sort of change in height, some sort of delta H, which will then turn into kinetic energy. When we're talking about electric potential energy, UE, instead of mass, we are going to be dealing with charge, and instead of height, we're going to be dealing with what we call electric potential. Okay, We'll call that delta V. So between these two plates, yes, there's a certain distance, but that distance helps us to calculate the strength of the electric field and the voltage. But so overall, the sum of delta V that's calculated as the object falls down. So it's based on charge and the potential difference. But let's talk more about what is electric potential exactly. And we could relate it to height, in fact, because when a charge falls through a potential difference, it gains kinetic energy. And in this diagram over here, well, we're looking at a representation of the electric potential of a positive charge versus a negative charge. Now remember, there are two types of charges. Masses is only one type of mass, so whenever you have a height, it just simply goes up. But whenever we're dealing with charges, a positive charge will always have a positive electric potential. A negative charge will always have a negative electric potential. Okay, so keep that in mind. Positive charges and negative charges have a negative V. So it's as if you're actually digging downwards when you're dealing with electric potential. And if you can imagine, if this is the positive plate over here, and over here, down here is the negative plate from the parallel plate that we were just looking at from before, that means when I put an external charge into that system, when I put that positive Q over that system, and it's gaining speed, it's literally as if it's rolling down the hill and falling down into that pit of the negative charge. Okay? But of course, we have two types of charges. So what's interesting enough is that while positive charges will fall down the electric potential, negative charges speed up by falling in the opposite direction. Okay? I know it seems a little confusing, but let's go through this a little bit more with a few other diagrams. We're going to be talking about equipotential lines. Okay? But before I talk about equipotential lines, I just want to take a page from Earth Science and review a topographic map quickly. In a topographic map, you have the lines representing different elevation changes. And you can see that in the picture of the mountain over here, as well as over here. Okay? Each elevation change, each line represents just another step in elevation change. And that's really what an equipotential line is as well. Whenever you draw the contour lines on a map, it's going to be similar. So, if this is just a side view of what a topographic map would look like, but it applies to how the charges are seen as well. So if I go back to this original picture from before, if I'm going to look at an equipotential line map or a contour line map, the lines would simply represent each of the different changes in height. Okay, and we're going to take a look at one right now. Okay, so here is just a picture of an electron, and we see that the electric field lines are going in. But remember, that electron, right, is really a giant pit of electric potential, of negative electric potential. So what these contour lines are representing are going deeper and deeper and deeper down inside that pit. You might be -2 volts falling downwards. Then over here it might represent -8 volts falling further down, -12 volts, -14 volts, but it's basically showing a pit based on the contour lines. And that's what we call equipotential lines. If you had a positive charge, that would simply be the opposite, where the equipotential lines are showing climbing up to the top of a mountain. But if you look at our parallel plate over here, so before we had one plate charge a certain value, another plate charge another value. Let's see. Let's say the top plate was charged with +4, let's make it +3. Yeah, +3 volts. And the bottom plate is a hole of -3 volts. So again, we're looking at our mountain going all the way down into our pit. So when we take a look at these equipotential lines, they basically represent the different heights, or really electrical potentials, at each point. So in this case, this could be +1 volt, -1 volt. This should go evenly, so I apologize for that. To make this work out better, 4 volts, 4 volts. So it'll be +2 volts, 0 volts, -2 volts. Okay, that works better. So in this case over here, right, each step on the equipotential line, because the equipotential lines are evenly spaced, is going to be another change in height as it goes down. If I were to take a look at my next diagram, okay, this is again the same representation of the hill with the pit of the negative charge. In fact, this is just a computer simulation from Wolfram Alpha, actually, that shows our positive charge on one side and our negative charge on the other side. And they're just playing around with moving the charges around based on the positions. But notice how you can see all the different contour lines, or really all the different equipotential lines, where you have different electric potentials, or heights, so we could call it. And notice, let me just go back for a second. I can bring it back here. When the positive charge is on top of the negative charge, that the hill will actually end up canceling out with the pit of the negative charge. Okay. So this is just another representation that you might see on the AP exam. We have equipotential lines. Obviously here, because we have a positive electric potential, we have a positive charge all the way in the center. And on the left, we have a negative electric potential, which means that we have some sort of negative charge over here. Okay? And whenever you're talking about some sort of delta V, whenever you're talking about some potential difference, some sort of electric potential difference, that's literally talking about going from one contour line to another contour line. So in this case, the delta V is going from 1 kilovolt to -2 kilovolts. So final max initial, -2 kV minus 1 kV would equal to, the potential difference is equal to -3 kilovolts, meaning that the charge fell down a total electric potential of -3 kilovolts. On the other hand, you could have a delta V of someone climbing up the mountain, and that would be a positive potential difference. Okay, there's one more example. Again, we have a positive charge over here, negative charge, negative charge. So in each case, you simply have these contour lines, or these equipotential lines, that represent what the electric potential is at each point. And of course, the positive charge and negative charge would be the highest point versus the lowest point, and everything else is just a gradient as you go from one to the next. Okay. So when we talk about electric potential, okay, electric potential is really just, we could relate it to height in a way, okay? It's basically the amount of, I guess, energy that would take, you could use to calculate the amount of energy it would take to move from one location to another. But because it is similar to height, it is going to be a scalar quantity. And rather than using W, and the formula that we wrote down before was that UE is simply equal to Q delta V. Okay, so that solves for the potential difference based on how much energy it takes to move a charge from one spot to another. So Q is going to be charge, electric potential energy, and potential difference. By the way, the unit for voltage or potential difference is simple because it's simply volts. Okay? The unit for energy, of course, is still going to be what it usually is, joules. And if I want to solve for the speed of the charge as it's moving from one electric potential to another, as it's falling from one location to another, whether it's falling down as a positive charge or falling up as a negative charge, don't forget you can set UE equal to KE. Okay, so we can set that equal to 1/2 mv squared, because all that potential energy is going to turn into kinetic.
Potential energy because it has the potential to do work.
Okay.
One way to build potential energy is to raise an object against gravity, like biking up a hill.
So this is an animation of just gravitational potential energy, but it's the same idea. If you take a positive charge and you're trying to climb the hill with the positive charge, it's going to take work to move it all the way up the hill. Or vice versa, it take work to take a negative charge and move it all the way down into that pit.
Once at the top of the hill, stored energy can now be used to do work. If a bike coasts down the hill, gravity then converts potential energy into kinetic energy, or energy of motion, by pulling the bike down the hill.
Okay. And we get the same idea. When the positive charge is all the way at the top of the hill, it will turn into kinetic energy as it falls down, but it takes work to get it up there in the first place. Or the negative charge, it takes work to get it down to negative electric potential, but then it gains kinetic energy as it falls upward. So another contour map, and for us is to do a couple of practice questions on this map. I know this map is not in your packet, but is nevertheless a good example. So take a look at the letters N and U. If I want to move, let's say, an electron from N to U, the question is, how much work would it take to move an electron from one point to another? Well, UE is equal to Q delta V. The charge of an electron is 1.6 times 10 to the negative 19 coulombs, times, in this case, delta V would be final minus the initial, so it would be negative 30 volts. So in this case over here, my final answer would be, it would take me a work of 4.8 times 10 to the negative 18 joules of work to move it from location N to location U. Notice in the end, I just leave my charge sign. In this case, I make the delta V an absolute value. Okay. Now, once the electron goes down into that pit a little bit, it took work to move it down. If I let it go, it's going to fall back up. So I could ask, well, the electron is now down here. As it falls back up to the other point, how much speed does it gain? Well, having the 4.8 times 10 to the negative 18 joules is great, and I can set that equal to 1/2 mv squared. So in this case over here, the velocity of the electron would equal to 2 times 4.8 times 10 to the negative 18 joules divided by the mass of an electron, which I know to be 9.11 times 10 to the negative 31 kilograms. I will square root that entire answer, and this ultimately would equal to 3.25 times 10 to the 6th meters per second. It's moving very fast indeed. Okay, so this is just an example of how to use a contour map or an equipotential map to solve for delta V, which allows us to solve for how much work it takes to move a charge from one location to another, and how fast it could be moving afterwards. Now, in this case over here, I just want to reiterate the path of the charge does not matter. Okay. In this case over here, let's say that we're taking it from location A to location B. Location A could have an electric potential of, let's say, positive 50 volts. B is further down the hill, so let's say it has an electric potential of positive 30 volts. Of course, the potential difference in this case would be 20 volts. But either way, overall, no matter what path you took, if you followed their path or if you went another path entirely randomly around, does the final electric potential change? No. So no matter what path you take, the potential difference is still going to be the final minus the initial, 30 minus 50, would equal to negative 20 volts. Okay? Doesn't matter if you went all the way down the hill and then turned around and went all the way up the hill, your delta V would be negative 20 volts. The path of the charge moving around does not matter. Okay. Let's do one quick practice question. Actually, let's do question 10. This is a good question over here. An electron in your TV tube. Now, remember before I had spoken about the electron gun, which shoots an electron at your TV screen. Or not the flat screens of today, of course, but the big tubes from just, I guess, 10, 15 years ago, actually. So in this case over here, what is the change in potential energy of the electron? So UE equals to Q delta V. So equal to 1.6 times 10 to the negative 19 coulombs times 5,000 volts. So the potential difference in this case is 5,000 volts. And we will end up with 8 times 10 to the negative 13 joules of energy. Sorry, 14 joules of energy. And if I want to solve for the speed of the electron, I would then set that equal to 1/2 mv squared and solve for the speed. Okay? So I'm just going to move on right now in the interest of time. Now, the next step we're going to need to do is how do we actually solve for how much electric potential there is, how much there is when it's being created by a positive charge or a negative charge. Okay, so before when we were talking about parallel plates, we had spoken about the formula E equals to V over D. And if I rewrite that, V can simply equal to E times D. If I could rewrite, we previously had a formula for E, which was KQ over R squared times D. D and R are pretty much the same thing, so they cancel each other out. So in this case, to solve for the electric potential, V is equal to KQ over R. Okay? But in this case, I'm going to write down also sigma V and sigma KQ over R. because if there's more than one charge producing electric potential, one makes a big hill, one makes a little hill. Somehow we're going to add those heights or those electric potentials up. So that's why we're going to use the symbol summation. Okay, you simply add them up. And because this is a scalar quantity, one simply makes it higher, one makes it lower. The most important thing to remember about this formula is that we include the charge sign. So this is the only formula to include a charge sign, because that charge sign literally tells us if it's high or it's low. Okay? So if we take a look at an example question, okay. What minimum work is required by an external force to bring a charge of 3 microcoulombs from a great distance away to 0.5 meters from a charge of 20 microcoulombs? To better understand that, let's look at this graphic right here. Okay, we have a big charge of positive 20 microcoulombs, and as you can imagine, it's basically a big hill of some sort of electric potential. And they ask us at a certain point that's half a meter away, how much electric potential is there at that point? Okay, so at 0.5 meters, if I want to solve for the electric potential, V would equal to KQ over R. It's a positive charge, so it's going to be a positive Q. So it would simply become 9 times 10 to the 9th Newton meter squared over Coulomb squared, but I'm running out of space, times 20 times 10 to the negative 6 coulombs divided by 0.5 meters. And this ends up equaling 3.6 times 10 to the 5th volts. Okay, so that's the height, or that's the electric potential, 0.5 meters away. Now they're going to bring another charge from a distant point. And that distant point simply means that we can assume that R is equal to infinity. So here's the first point they're going to bring it to. Well, they're going to bring it to. That distant point, I'm going to say, I'll just draw all the way over here. We don't know where it is, but it's far away, and R is equal to infinity. Well, how much electric potential is there at that distant point? If I use the formula V equals to KQ over R, anything divided by infinity automatically equals to 0 volts. So now, if I want to move a charge from point A all the way to point B, what's the potential difference? Well, in this case, final minus initial, so 3.6 times 10 to the 5th, so delta V will be simply equal to 3.6 times 10 to the 5th volts. And the charge that we're moving that they had mentioned was a 3 microcoulomb charge. So if I'm moving a positive Q from here to here, to find out how much work that takes, I use UE equals to Q delta V, so equal to 3 times 10 to the negative 6 coulombs times 3.6 times 10 to the 5th volts, which equals to 1.08 joules. So the amount of energy it would take would be 1.08 as I'm moving that small positive charge up the hill to an electric potential of 3.6 times 10 to the 5th volts. Even if I have multiple charges, I should still be able to solve for the total electric potential at each point. If I wanted to figure out what the total electric potential is at A versus B, well, let's just do A first, okay? If we have two charges, that means we have V1 plus V2. We have to find the total electric field. This distance over here, if you use Pythagorean theorem, is equal to 60 centimeters. And So at A, the total V electric potential at A will be created by the first charge of 50 microcoulombs. So it would be KQ1 over R1 plus KQ2 over R2. So that would equal to 9 times 10 to the ninth times 50 times 10 to the negative 6 coulombs divided by 0.3 meters plus 9 times 10 to the ninth times negative 50 times 10 to the negative 6 coulombs divided by 0.6 meters. In this case, my total electric potential created by the hill and the pit combined all together would equal to 7.5 times 10 to the 5th volts. So this is the total electric potential at A. B is a little bit easier. So if you guys notice that distance from the first charge to B is the same as the distance for the second charge to B. So if I work it out, I'll note that because these are equal, so when we're doing for B, because KQ1 over R1 minus KQ2 over R2 are exactly the same, Q is exactly the same R's, they actually become 0 volts. So the total voltage at B is equal to 0 volts. So if I want to know what's the potential difference from A to B, it's simply equal to the final minus initial, or in this case, negative 7.5 times 10 to the 5th volts. So normally I would leave that as an absolute value, of course. Okay? If I want to move an electron, let's say, or let's say move from A to B, okay, how much work would that take? Well, that would simply be UE equals to Q delta V. So that would equal to 1.6 times 10 to the negative 19 coulombs times 7.5 times 10 to the 5th volt. And that gives me a final answer of 1.2 times 10 to the negative 13 joules. Okay? So that's how you combine solving for the electric potential with solving for the electric potential energy. Right now, we're going to take a look at the same problem a slightly different way with this diagram. This diagram does represent exactly what we had solved for before, as a positive charge and a negative charge placed next to each other. Again, just note that at point B, the total electric potential at point B was equal to 0. And you can see that actually everywhere along this gradient line, the total electric potential equal to 0, because the positive electric potential of the hill cancels out with the electric potential of the pit of the negative charge. Over here, we can see that at point A, when we had solved for the electric potential at point A, it's higher up the hill. So ultimately, when we took our electron and we moved it from point A to point B, it took a certain amount of work based on the potential difference between point A and B.